Hi, welcome. This is going to be the 10th lecture in the series on metric spaces. And today what we are going to do is we are going to talk about the algebra of real valued continuous functions on a given metric space. Usually, uh, in my courses, in my lectures on continuity, I give my definition of metric spaces in terms of sequences, right? The very first lecture. And immediately I prove what I'm going to do today. But this time we waited quite some time. Okay, at least 2 lectures or so. In the third or fourth lecture, we are going to do that. Is there a reason for that? Yes. The reason is in this course, we decided we have a list of examples using, okay, whenever a new concept is introduced, we will illustrate the concept in those examples. So that was top priority for me. So naturally, I did all those things, right? We are going to talk about algebra. And just before that, let me start with a very easy observation about composition of continuous functions. Okay, so let us get started. Okay, the fact we want to talk about is the thing. So I have a metric space xd, yd, and zd. Okay, this is my x, this is my y, this is my z. Okay, so I have f from here and g from here. So I have a point x here, I have a point y equal to fx here. All right. Okay. So what is our assumption? Our assumption is f is continuous at x and g is continuous at y, where y equal to f of x. F is a function from x to y and g is a function from y to z. Okay. Now what is the next? So I have naturally a composition from x to y. These are all, sorry, x to z. Question is g commutative continuous? Where? At x, at this point. So I have this function, right? Okay, to prove continuity, what is that I have to do? At x, you give me a sequence xn in x with what property? Xn converges to x. What am I supposed to show? I'm supposed to show fxn converges to, sorry, g commutative at xn converges to g commutative at x. Right? Because the function whose continuity is g commutative. So I'm doing that. Is that all right? Okay. Now, yeah, see, it is here. I was searching for it. Okay. That's my mistake. So we wasted time. Anyway, come back. This is very easy. Why? Now xn converges to x and f is continuous at x. So f of xn, where does it? It belongs to y. And what happens? Fxn converges to fx. That is, this is also in y. Right? So I know fxn converges to fx. Right? Now you can think of this as a sequence yn which converges to y. Okay. Now what do I know about g? G is continuous at y. Therefore, g of yn should converge to g of y. Yes? Right. But what is g of yn? G of yn, g of f of xn. Where does it converge to? G of y. That is g of f of x. But this is by definition g converges at xn. Okay. So we proved the result. So pause, review, and proceed. Okay. See, most of the time, what students don't appreciate, I've seen it even at a very high level, even at faculty members level, is composition is a fantastic trick. So if you want to show something about a function, one of the easy ways is to see whether it is composite of some easier functions. Okay. And you may know the properties of the composing functions, easier, the component functions. From that, you may be able to conclude the property of the composite. Okay, it's like in a molecule, you break it into atoms, you understand atoms, how they work with, so that you have some kind of an idea about molecule. Okay, so for example, in differentiation, multivariable calculus, chain rule is one such. So you have to become adept. When you see a function, try to see whether you can think of as a composite of functions. Maybe things become simpler. Okay, please keep this in mind as you go along. Okay, I will show that in a minute. Okay, to show the power, I am going to do algebra of continuous functions using this composite rule, even though I will also give you direct proof. Okay, let us start with the very simplest case. Suppose f is a function from x to r continuous on x if you want. Then I want to know whether mod f is continuous. So what is mod f? Mod f is a function from x to r. So I have to tell you what is its value. See, this kind of thing is never defined. You simply write mod f x. That's why I'm writing. Mod f x at this must be a real number. What is that real number? That is this real number. Modulus of the real number. You see that? Therefore, mod f is a function from x to r. So what is the question I'm asking? Mod f is continuous. Now, what do you think I should do? Look back what I said. I have to think of it as a composite of some easy functions. What are the easy functions I can think of? So f is from x to r. F, and from here, modulus is a function from r to r. Right? What is the composite? X goes to fx, and where does fx goes to mod fx? But that is this nothing other than mod f. You understand this? Therefore, mod f is composite of two functions. Absolute value function, composite f. This is just absolute value function. Now we know this is continuous. To prove this is continuous, I have to check whether this is continuous, but all of you know that. Okay, just to be on safer side, suppose Tn is a sequence of real numbers Rn, okay, and T is in, sorry, R, T is in R. What do you have to check? If Tn converges to T, I have to check whether mod Tn converges to mod T, right? This we had already seen earlier, because mod Tn minus mod T, I have to estimate. So how do I estimate this? See, so mod Tn, I do not know how to estimate this. I know how to estimate this. By triangle inequality. Therefore, mod Tn minus mod T is less than or equal to mod Tn minus T. Right? And interchange in this Tn and the T interchange, then I will have mod T minus mod Tn is less than or equal to this T minus Tn, but it is same as Tn minus T. You understand? So what does this show? This goes to 0. Therefore, I proved it. You understand this? Okay. So I proved the continuity of the modulus function. Therefore, this is continuous and this is continuous. Therefore, this is continuous. Do you understand? Pause. Review. Okay, PRP. You understood? Look. Now comes the icing on the cake. Now suppose f and g from x to r are continuous function. If you want continuous at point itself will do, but I will do general. If f and g are continuous at x, I am going to prove f plus g is continuous at x. Okay. So now I define a new function f plus g, which should be a function from x to r. So I have to tell you what is its value of g at x. This must be a real number. How do I get this real number? You get this f is a function, therefore fx is a real number, gx is a real number, add them, that is. So I define f plus g. Okay. These things we are defining, okay. Many teachers do not take pain to explain this kind of thing. You think it's automatic. No. We know how to add to real numbers. Now we know how to add to functions which take values in real number. How it's done? It's done like this. If you had attended my lectures on vector spaces and in linear algebra, you would have seen I had explained these things there also. Anyway, right? I want to say this is continuous, right? Okay, let us give an easy proof first, then I will give a little more sophisticated proof. The reason why I want to do is to easy proof, you should know that very easy. And why I want to give a sophisticated proof, that is the way students can improve their standard, right? If I always think I will always give easy so that it will be easier for you, you will not, your standard, your level of understanding cannot raise. It's like saying, I said in earlier lecture, one of the lectures, if your parents keep talking only very, very simple words and a sentence consisting of only 2 or 3 words, then you will never pick up to speak good language. You understand? So the way is slowly we have to improve our standard. That's what I'm going to do. Okay, let us first easy. What is the easy proof? So you give me a sequence, fix an x in x. I have to prove continuity of f plus g at x. Give a sequence xn in x. With what property? Xn converges to x. What am I supposed to prove? F plus g at xn, where it is converged to f plus g at x. Right? But what is f plus g at xn by definition? It is f of xn plus g of xn. What is this? This is by definition f of x plus g of x. So I have to check whether they continuous. This converges, right? But what do I know? F is continuous, xn is a sequence such that xn converges to x. This implies fxn converges to fx. This is a sequence of real numbers. Similarly, gxn converges to gx, right? Now these are two sequences of real numbers which converge, therefore their sum also converges. That is fx plus fxn plus gxn converges to fx plus gx. Okay, so we proved f plus g is continuous. You follow that? Now what is the, okay, slightly more sophisticated proof? Because this proof will be useful when you go to topology also, more general version. But anyway, let us do that. Okay, now let us look at from here. Now I am cooking up. You see that? I am going to bring in composite of functions, not only composite of functions, continuous functions, continuous. I am also going to use some of the results which we talked about, continuous functions from a metric space into Rn. I am going to use that fact. You will see that to R. What is the function? Start with any x, send it to an ordered pair of real numbers. What is it? Fx gx. Now what do I want? I want this function should be composite. So what should I write? This is addition. That is, this is the map u comma v going to u plus v. Do you understand this? Yes or no? So this is the map. My plus g map is, call this map as phi. This map is xi. Therefore, what is phi of x? Phi of x is fx gx. And what is xi of x? So, sorry, xi is from R2. Therefore, xi of uv is u plus v. You understand? Is a composite. Do you see that? Composite xi composite f is f plus g. Sorry, composite phi is f plus g. Is that clear? Because you started with an x, under phi it goes to fx gx. Under xi, where should it go? It goes to the addition. Therefore, I got it. Yeah? Are you sure? Make sure you understand. Okay, good. Now we are through. What do we know? So, is phi continuous? That we know, because if there is a function f from x to Rn, and if I write f equal to f1 to fn the component functions, I know f is continuous if only which fi is continuous. Therefore, is phi continuous? Is same as asking whether the component functions are continuous. What is the first component of phi? F. Is that continuous? That is given. Similarly, g. Therefore, phi is continuous. Okay. Now we had also seen in Rn to R, we have proved addition, R2 to R addition, multiplication, etc. are continuous. Do you remember that? That was one of our, I think, the first lecture itself on continuity on Rn to R. We have done that. And is xi also continuous, right? Therefore, the composite, which is equal to f plus g, is continuous. Okay. You see that the earlier proof of how easy it is. As soon as I define the definition of continuity, I could have proved f and g are continuous functions, real valued continuous function. F plus g is continuous. You understand this? To make you appreciate if f and g are continuous from x to y, y is some arbitrary metric space, there is no way of defining f plus g. Do you understand that? Yes, there is no natural way of defining f plus g if this is some arbitrary metric space. Whereas if it is a real valued, I can do that. Yeah, please appreciate. And if you want to really go for higher mathematics, try to learn this kind of sophisticated proof. Okay, it will enhance your thinking. It will give you an in-depth understanding of mathematics. Okay, now what is the next one? Next one is also easy. What is the easy one? Okay, continuous, c is a real number and c times f is from x to r. What is c times f at x? I know all of you know that c times f, this is a product of two real numbers. Okay, what is the easy proof? Xn converges to x. I will go fast. Then cfxn, does it converge to cfx? Okay, but what is this? C times fxn. I want to know whether it converges to c times fx. But what do I know? Fxn converges to f because f is continuous at x. And what do I know? If a sequence of real numbers converge to a limit, then scalar multiple of that sequence also converges to scalar multiple of the limit. Yeah, therefore this is okay. Therefore I proved CF is continuous. Am I fast enough? Yeah, okay. Now what is the sophisticated proof? Sophisticated proof is the following. Okay, can I think of a sophisticated proof for this? Let me see. X going to fx. Okay, that's it. And then from there I'm multiplying by g. That is from R to R, right? So x going to R and from R to R. What is this map? X going to fx. That is this map. What is this map? U going to c times u. Right? Okay, call this as phi and this as xi. Phi is nothing else than xi. Yep. And xi is this map. Xi of u is c times u. And what is xi composite of? Xi composite of, xi composite of phi at x equal to xi of phi of x. Phi of x is same as f of x. Xi of a real number is c times f of x. Therefore, it is c times f. You understand that? Therefore, xi composite phi equal to c times f. And is this continuous? Because x going to fx is continuous, no problem. And we had already seen multiplication is okay. Scalar multiplication is also continuous in Rn. Remember Rn to R given a vector x, c times x is continuous. We proved it. Therefore, this is continuous. This is continuous. This is continuous. Composite is continuous. Therefore, this is continuous. Okay. Okay. The third is we want algebra, right? So again, f and g continuous real valued functions on R. Then I want to define a new function fg from x to R. This is just a notation. It must be a function. What is its value at x? This must be a real number. How do I get a real number? I know fx is a real number, gx is a real number. I can multiply them in R. Therefore, this is the definition. Yeah. And I'm sure all of you know the easy proof now, right? Xn converges to x, fg at xn, that is fxn, gxn, does it converge to fg at x, that is fx into gx, but I know fxn converges to fx and gxn converges to gx and fxn converges to fx. Therefore, the product converges to, because algebra of convergent sequence of real numbers. Do you follow that? But what is a more sophisticated proof? How many of you can think of? I give you some time. Yeah. What is the sophisticated proof for this? So what should be the map? I'm sure that all of you know what should be here and what should be here. What should be your y? Look at the way I define addition. It is r cross r. And here it's r. And what is this map? X going to, as earlier, fx into fx gx. This is ordered pair of real numbers. What is this map? Remember, what do I want? Call this as phi. Xi, I want to say xi composite f. Sorry, xi composite phi must be f times g. What should be my xi? Start with the uv. Where does it go to? U times b. That's a multiplication, right? Now you know phi is continuous. In the addition case, we saw y is continuous. And we had already seen the multiplication map from R cross R to R is continuous. Okay, in the first lecture. Therefore, xi is also continuous. And the ordered pair is the xi composite phi is nothing other than f times g. Therefore, f times g is continuous. Okay, pause, review, proceed. What is the last one left out? That is the inversion. Suppose f is a function from x to r, continuous, and let's assume fx is not equal to 0 for x and x. Okay, if you want it to domain a also, you can take, it doesn't matter. Then I want to define a new function 1 by f from x to r. I have to define 1 by f, its value at x equal to what? So it is equal to 1 by fx. And since fx is non-zero, this makes sense. You understand that? So what is that I have to prove? If f is continuous, 1 by f is continuous. What is the easy proof? Okay, without, I will not say f1 etc. You know that. I have to check whether. But what is this? What is this? Why this is true? Because you know, if a and c sequence are real numbers which converge to a is not 0, a is also not 0, then you know 1 by a and converge to 1 by a. Algebra of convergent sequence of real numbers. Therefore, this happens. Are you following? We already used it earlier also. Okay, r star to r star, t going to 1 by t is continuous. The same argument we proved there also. Now, what is the sophisticated proof now? How many of you can think of? So I have x to r, but remember it's actually lands in r star. So f going to, sorry, x going to f of x, and this is actually r star, and it goes to r. What is the map? This is map u going to 1 by u. Okay, this is phi, this is my xi. I know this is continuous. We had already proved this is continuous. Therefore, what is the composite map? X going to fx, that goes to 1 by fx. That is 1 by f is continuous. Okay, please go through once or twice. If you want to go for higher studies in mathematics, I would request you to go through both the proofs. You should be confident. You can see how easy it is. This also tells you, given a function, how to think of as a composite of functions. It may not happen all the time, but if it happens, you should see whether life becomes simpler. Yeah? Okay. Now, very good. Now we look at the, so what have we shown? So let us look at C of XR to be all functions from x to r which are continuous on x. So what have we shown now? If f and g belong to that, f plus g belong to this, and if c is a constant, c times f belong to this, and okay, these two things already show that this is a vector space over real numbers. Yes, do you agree with that? Okay, right? Okay, next we also have something more. It's also a ring. Ring is what? It has two operations. One is addition. It's a commutative ring because this is, sorry, not commutative ring comes later. The under addition, it's an abelian group. You understand that f plus g is same as g plus f. Okay. I also say this is not only a real vector space, it's also a ring. Why it's a ring? Because f and g is there, f times g is also there. Is there a ring with unity? Ring with identity, multiplicative identity. Yes, because look at the constant function. This belongs to C of XR. You understand? Therefore, it's not only a vector space over R, it's also a ring, commutative ring, because F times G is same as G times F. It's a commutative ring with identity. Yeah? Do you accept this? Okay. And suppose X, okay, is it all right? Okay. Now I want to go back to the earlier thing. Do you remember in last lecture, I started with the question, you give me two distinct elements X and Y. I wanted to know whether there is a continuous function F from X to R so that F takes distinct values at X and Y. We said yes. We answered this also, right? Now the question I want to ask is slightly different. So I have a metric space X and I have a closed set A and I have a closed set B, and said that A and B are non-empty. A intersection B is also not empty. If A intersection B, A is not empty, B is not empty, and A intersection B is empty, and A and B are closed. You understand that? For example, if A equals singleton X, we know that any finite subset of a metric space is closed. Therefore, it will be closed. Similarly, if Y I take to be the singleton Y to be B, then B is also closed set. Their intersection is empty because X is not equal to Y. Then what did we find? We found a function F which takes distinct values at X and Y. So okay, I can ask a similar question. Do you understand this? So I want to know whether there exists a real valued continuous function from X to R so that, okay, F equal to, let us say, 0 on A and equal to 1 on B. This is continuous, right? So how I have to construct such a function? Remember, for this, how did I construct such a function? How many of you remember? I defined the thing F at Y to be distance between X and Y. You understood that? Yeah. Now think of it. Look at this. How many of you have intuitive feeling how I should define F? How to construct such F? What kind of continuous function I should look for? How many of you can imagine that? I'll be happy if at least some of the viewers, at least 10% of the viewers have a guess. Remember, we have defined the distance between X and A, where A is any set. You understand that? Yes? So we are through. So somehow we should construct such an F out of these things. Idea is construct F out of these two functions. We know this is continuous, this is also continuous. You understand that? Okay. Now again we had observed A and B are close. Then we have shown that Z belongs to A if and only if, so distance between Z and A is 0. And similarly Z belongs to B if and only if distance between Z and B is 0. You understand that? Right. Now let's look at, suppose I look at dz. Okay, let me define fx equal to distance between x and a. Suppose I do that. Okay, then f of x is 0 if x belongs to a. So I got it. You understand that? This one. Now I want a b. Okay, if x belongs to b, what happens? F of x equal to distance between x and a, right? And this cannot be 0. This must be positive. Why? If it is 0, that means x belongs to a. And x belongs to a as well as x belongs to b. That's a contradiction because a and b are disjoint. Right? Therefore, and remember that we are using the fact they are closed also. You understand? Therefore, I seem to have got at least a function which distinguishes a and b. That is, f is 0 on A and f is positive on B. Isn't it already good enough? You understand that? Therefore, f is 0 on A. F is of course a continuous function. Where to where? X to R. And f is positive on B. So at least it seemed to take distinct values. I may be happy with that. Yeah. But I was a little greedy. I asked for it should be 1 on B. Right? So if I want to make this 1, what do you think I will do? An obvious thing is to make dxa by dx. What will I do? Dxa. But then when x is in A, this is 0 by 0. This has no meaning. Are you following? Therefore, I may try with dxa by dxa, but I know dxb. You understand that? Okay, this will not work. And similarly, dxb by dxb also will not work, because when x is in the corresponding closed set, this will be 0 by 0, right? So if I may try to write dxa by dxb, but then that will be something else, because for x is in b, this will be 0, dxa by dxb. So this also will not work, because if x is in b, this will be positive, but this will be 0. Therefore, it will not be a real valued function. Do you understand? Therefore, continuity is not assured. Are you following? Please pay attention. Yeah. So that suggests, let me look at this function. So let us define fx equal to distance between x and a by distance between xa plus distance between xb. Okay, there are a lot of things I have to check. Okay, but let's not worry about, okay, whether this function makes sense or not, whether it's continuous, etc. Do you remember? I just like to see whether the function works. After that, let me check continuity. Okay, I have to make sure whether even the function makes sense, because the denominator may be 0. When is the denominator 0? Denominator is 0 if and only if dxa plus dxb is 0. That is if and only if dxa is 0 and dxb is 0. Why? Because these are non-negative numbers. Sum of two non-negative numbers is 0. That means each of them must be 0. But this means x is in A and x is in B. That is, x is in A intersection B. But that's empty, right? So therefore, this contradiction shows this is never 0. This cannot happen. Okay. Therefore, this is a function. This is a real valued function, right? Now, okay, what is f at if x is in A? What is fx? See, fx will be x is in A, therefore numerator will be 0. dxa will be 0. Now the denominator dxa plus dxb, but remember x is in A, therefore this will be 0, but then dxb is actually positive, therefore it is 0 by dxb. Okay, 0 by dxb, which is for x in A. If x is in B, it will be dxb. Sorry, dxa by dxa plus dxb. But notice that if x is in B, this fellow is 0. Therefore, it is dxa. Remember, yeah, A is closed, x is in B. Therefore, x is not in A, because A and B are have empty intersection. They are disjoint. Therefore, if x is in B, x is not in A. Therefore, dxa must be positive. By dxa, that's also positive. Therefore, it's equal to 1. You follow that? Okay. Next, what is remain? So f is a real valued function x to r, so that f equal to 0 on A and f equal to 1 on B. And the next thing is it continuous? Is that clear why it's continuous? because this is x going to dxa. This numerator is a continuous function. And look at this denominator. That's a continuous function which is non-zero, right? The denominator, look at that. This is dxa plus dxb. This is continuous because sum of two continuous functions, and it is always positive. We have seen it. Therefore, it's non-zero. Therefore, 1 upon that, x going to this is continuous. And x going to dxa, this is continuous. Therefore, product of these two functions, f type g, that is continuous. That is our function. Yeah. Therefore, what have we proved? We have proved this is a famous result due to Urysohn, but he proved in a much more general case, which is usually known as Urysohn's lemma. Let xd be a metric space, a and b be non-empty, closed subsets of x such that a intersection b is empty. Then there exists f from x to r such that f is 0 on its continuous function, f is 0 on a and f is 1 on b. There may be many. One choice is this, namely fx equal to d of xa by d of xa plus d of xb. It's a choice, but it only says there exists some function. Okay, I hope you all understand. And this is this all we have to say about real valued continuous functions. And usually this is not even done, Urysohn's lemma, and even dxa is sometimes not mentioned. Okay, now I think you are all richer in mathematics. Yeah, you like it? Very good. I think that's about all the things I wanted to teach you about metric spaces. There are 10 lectures I had given. This is more than enough for the time being. Okay, there is a little more I can say about density and how it's related to limits and closure of a set. Okay, sometime later I will take it up. But if you want, you can continue now with respect to equivalent conditions, characterization of continuity in terms of epsilon delta. We are done it through. Let me stop it. Yeah. So these 10 lectures have a very concrete thing. And if you are done, you can read any book on metric spaces or your class notes. You can attend your lectures. You will follow much better. And there are a few more things I may like to say, something about density, closure of a set, etc. Sometime I will do it. And the next thing is, remember, my definition of continuity used to the sequence. Usually one calls it sequential definition. There is also standard epsilon delta definition. There is also a definition in terms of inverse image of open sets. Okay. And these three are equivalent. I think I have another video which was recorded about 4 months ago on continuity on metric spaces. Please follow it, this video with that video. I will also have a look at that because I was just learning how to record those things. So it may or may not be good. So if you have problem with that recording, please leave your comment here. Okay, or you have my email ID. You please send an email. I will re-record such a thing. Okay. Otherwise, for the time being, this is the last lecture of the series. I hope those of you who wanted metric spaces are happy that you learn and you learn thoroughly. Please leave your comments because that will tell me how appreciative you are about this thing. This will keep me motivated. I hope you understand. Yeah. Okay, great. So we'll stop recording. Have a good day. Take care. Stay safe.